Okay, so now that we've talked about what is a logarithm and we've evaluated some logarithms without a calculator and with a calculator, we want to talk about the graphs of them. And again, you're going to need to be able to graph these both with and without a calculator, both with and without technology. Today we're going to focus more about like doing it by hand without a calculator, maybe a scientific calculator to do this. So again, we're getting close to those applications. So remember that logarithms and exponential functions are inverses of each other. So remember we talked about inverses already, and that means they're symmetric about the line y equals x. And not that you have to graph both of the inverse and the log every time, but I just want to kind of show you how you can graph these and the connection here. So think about if you were going to graph this exponential graph, right? If we were going to pick some x values here, like if I picked -1, 0, and 1, those represent the exponent. So I just plug in the exponent, 2 to the -1 equals 1/2. When I plug in 0, I get 2 to the 0 equals 1. When I plug in 1, I get 2 to the 1 equals, not 1, equals 2. So when I graph that over here, we get that exponential graph. At -1, it's at 1/2. At 0, it's at 1. At 1, it's at 2. And we could even go further if you want, right? At 2, you would get 2 squared, which is 4. And I'll even do one more at 3. 3 squared, 2 to the 3rd is 8. 1, 2, 3, 4, 5, 6, 7, 8. So we get that nice exponential graph that we worked on all last week. Exponential growth model, right? Well, if you remember, that inverse functions are symmetric about this line. I forgot that I don't have to do this. The line y equals x, right? Oh, that's kind of crazy. Which means that this graph should flip over that line, which means inverses, the x and the y switch places. So think about if I made an xy chart here. Now, x does not represent the exponent anymore. X represents the answer. Or think about if you rewrote g of x using that definition of a logarithm, where g of x, I'm going to say g of x is y, then we would get 2 to the y equals x. So now x is your answer to that exponential problem. So we could pick 1/2, and that's saying, right, if I wrote this out here, log 2 of 1/2, that's saying what exponent gives me 1/2. 2 to the what equals 1/2, and the answer is -1. I could pick 1, and again, think about what this says. This is saying 2 to what power equals 1. So the x's are now the answers, and the y's are the exponent. So remember, a logarithm is just an exponent. So 2 to the what equals 1? Well, that's 2 to the 0. And if I picked 2, log 2 of 2, 2 to the what equals 2, and the answer is 1. And again, I know you have Desmos, I know you have calculators, but there will be some graphing on the no calculator portion of the test, and it would look something like this. So just kind of looking at these, if we graph these now, at 1/2, we're down here at -1. At 1, we're at 0. And at 2, we're at 1. And again, notice that these domains and ranges have switched. We could even say at 4, 1, 2, 3, 4, we would be up here at 2. And this is going to go up really, really slowly like this. So this blue graph is my g of x, where the red graph is my f of x. And just like with exponential functions, we can translate and reflect and all that stuff too. But the g of x there is like your go-to graph there. Okay? So just like talking about e to the x, we want to talk about ln of x, and this would be where you'd want to use a calculator. It says find the domain, the x-intercept, and the vertical asymptotes, and we're going to talk about that in a minute. But remember that ln is just base e, but obviously I wouldn't make you do this without a calculator. But if I was going to graph this, I would pick some numbers here, and we could pick just like 1, 2, and 3. You could also pick E if you wanted to, right? I'm going to pick E first, and then I'll pick real numbers. I mean, E's a real number. But if I did ln of E, remember that's our lovely property that ln of E is just 1. Remember that E is like 2.7 something. 2.7 something. So think about if you pick a number smaller than E. So I guess 1 is a good one to pick. That's also a property. That's e to the what equals 1. That's going to be 0. If we picked a number even smaller than that, think about if we picked, I don't know. Well, let's just pick 2. And that's where I'd have to, on my calculator, type in ln of 2. And I would get 0.693. And if I pick a number bigger than E, so let's say I pick a number like 4, and again, I'm just typing that on my calculator, I get like 1.4. I don't know why I need to go to 3 decimal places when I'm just graphing. So if I graph this at E, which is about 2.7, I'm going to go up here to 1. At 1, I'm going to go to 0. Less than that, I'm going to get when I go to, what did I do wrong here? Oh yeah, that's right. At 2.693, that would be like right here. Those are really close together points. And then way out here at 4, I would get 1.4, I'm going to say is like this. Excuse me. So just like our last one, our log base 2, it's going to go up like this. And also, so you think about the exponential graph, e to the x has a horizontal asymptote, so it should make sense that ln of x is going to have this vertical asymptote. Also think about when you take a logarithm, you can't take the log of a negative number because there is no negative numbers that you get out of an exponential graph. And so they'll always have a vertical asymptote. So thinking about these things, again, if you know the domain and range of exponential functions, we're just switching it for this. But the domain of this is not all real numbers because we're stopping it right here, right? If there's a vertical asymptote, the domain is not all real numbers. So the domain is what is the smallest value we can plug in there. Well, we can't even plug 0 in there, right? 0 is our asymptote. So our domain is not including 0 to infinity. Think about in exponential graphs, we talked about the y-intercept. So now we flipped it. So now there's going to always be this x-intercept, and that's because the log base anything of 1 is 0. So our x-intercept should always be 1. And the vertical asymptote is going to be where that domain starts. And again, unless there is a transformation that's sliding this to the left and the right, our asymptote is going to be the line x equals 0. Now, if we slid that to the left or right, then our asymptote could change. All right, your book does a lot of log base 10 and ln of x because they're wanting you to use calculators. I want you to be able to do both, so I wanted to make sure that we did some of this with a calculator. So the last one here that I want to graph is a log base 10, but it's also one that has a transformation. And again, I know you can use a calculator in log base 10, but I'm telling you that I'm going to give you some to do without a calculator. And so I want you to be able to think about what kind of number should I pick if I didn't have a calculator. And so just like with exponential graphs, my advice to graph them is always pick what makes that go to 0. It's kind of the same idea on this one. What makes that go to 0 will be your vertical asymptote, and so you're not going to be able to pick anything smaller than that. Also think about our transformations. The fact that that's an x minus 3 means that that's moved to the right 3, which means our asymptote has moved right 3. So if you tried to on your calculator to plug 3 in here, it's going to say that there's a domain issue, right? That's our asymptote. So what kind of numbers should you pick if you don't have a calculator to make it work out nice? Well, think about this is log base 10, so you want to pick things that are going to give you powers of 10, right? So one of them that we could pick always is what gives us 1 here. So what if I picked 4 for my x? And I'm going to write this out over here. I would have negative log, and I'm going to put the 10 there just so you can see it. And then I would have 4 minus 3, which is negative log of 1. And again, that's a really good one to pick. It's just like picking something to the 0 power, because log base 10 of 1 is what exponent do I need to have a value of 1? And the answer is 0. Well, negative 0 doesn't exist, so that's just 0. So always pick what's going to give me the y value of 0, or what's going to give me this to equal 1. And then I pick the base, so I would pick 10 next. If it was log base 7, I would pick 7 next. If it was log base 5, I would pick 5. And then I pick the what would give me the negative exponent. So if it's base 10, then I pick 1 over 10. Oh, wait a minute, that's not going to work, is it? That would work if this was just x, because if I had negative log base 10 of 10, I can do that without a calculator. But because there's a transformation, I have to pick what's going to give me 10. So think for a minute, what number should I pick here so that when I subtract 3 that I get 10? 13, right? Because if I pick 13, then I have 13 minus 3, which gives me negative log 10 of 10. And again, you got to be able to do this without a calculator. 10 to the what power equals 10? Well, the answer is 1, but this negative in front means that the answer is negative 1. And think about that transformation. The negative in front means it's going to flip over. And again, I picked 1/10 up here, but that's not right, because 1/10 minus 3 is going to be undefined. I got to pick what number is going to give me 1/10 in that problem. Is that just 3 and 1/10? And again, do the math here. 3 and 1/10 minus 3, doesn't that just give me 1/10? And again, I'm picking that because I can do that one without a calculator. 10 to the what power equals negative, or equals 1/10? Well, that's negative 1, but this negative out front is actually going to make that positive 1. And again, it's because we're flipped over here. So if it helps you, you could draw in your asymptote here at 3. That means our graph should never cross that line. And then at 1, it's going to be, sorry, I'm doing that backwards. At 3 and 1/10, it's going to be up here at 1. At 4, it's going to be at 0. And all the way out here at 13, this is 10, 11, 12, 13, it's going to be at negative 1. Now this one definitely doesn't look like our last one, but that's because of this negative. It's reflected. It still has that vertical asymptote, but now it's pointing up. And then this side is going to come back. And again, we've just flipped that over, which is why understanding those transformations is so important. We're going to practice graphing some more of these in class, and you're going to practice. Again, don't get bogged down by cheating on Desmos. Check on Desmos, but you want to be able to do this by yourself as well. Okay? So I think one of the last things I have here, oh yeah, this is the last thing. Just kind of wrapping it up. We did this with exponential graphs. With log base A or ln of x, same thing. Remember that ln of x is just log base e of x, so e is just a special number. But every time, the domain is going to be where that vertical asymptote is. So I'm going with these basic graphs. I'm calling these the parent graphs. This domain would change if there's a transformation. But the domain of these parent graphs with no transformations will always start at 0, because you can't take the log of a negative number. You can't take the log of 0. And the range is now all real numbers because there is no horizontal asymptote, right? The domain and the range have switched. Our x-intercept is now 1, 0. These basic graphs should be increasing and continuous. And again, the vertical asymptote is going to be the y-axis unless there is a transformation. So today is a lot more graphing, or at least questions about graphs. This is the homework. Again, please pre-label your paper if you watch this video before class. And I believe 43, 45, and 49 are the 3 that I want you to graph. We'll look at those in class, but disregard the other directions if they say something else. All right? Oh my gosh, why can't I get this to stop? Where did it go?